Hello, students. Hello, guys, can you hear me? Hello, can you hear me, guys? Hello, hello, guys, can you hear me? Hello, hello, guys, can you hear me? Guys, can you hear me? The students, can you hear me? Hello, guys, can you hear me, guys? The students, can you hear me? Am I audible to you? Okay, let us get started. Oh, I'm unmuting all of you. Just a moment. Parents, mute all. I'm muting all of you guys. Okay. If you have anything, just put a message or let's continue. Spams. Okay, guys. I'm gonna start the lecture. So welcome all of you. So just a moment. Yes, I'm audible to all of you, right? Okay, let me start.
Yeah.
Okay, let me start. I'm muting all of you. Okay. Okay. Welcome, guys. Welcome to the lecture. So I think probably you're seeing me for the first time. I'm Dr. Srinivas Rao. I'll be teaching you remaining for 2 units of concrete technology, unit 4 and unit 5. So Let me start with a little introduction. Unit 4. So I joined our institution very recently. So I think probably this is the first lecture from my side. Okay, guys. Before we start the fourth unit, let me see. Let me briefly recap what you learned in the first three units. To start with, probably start with the first unit with the cement. Probably with manufacturing of the cement and other properties of the cement. Okay, then basic test you connect on the cement, all that you learned in the first unit. And comes to second unit, probably we studied more about aggregates and how, just a moment, guys. So we talk about aggregates. So in the aggregates, we talk about the different properties of aggregates, their properties and all that you studied. And come to third unit, I think you studied uh, mostly admixtures and then frustrate of the concrete. Then you studied the creep and shrinkage, all the properties. Now in the fourth unit, we'll be talking about hardened concrete. The hardened concrete, we'll talk about science behind it and some of the properties and tests and all on this. And let me tell you the learning outcome of this unit. Learning outcome in the sense, it's basically tell you what you'll be able to do after completely going through this module. For this module, the first module on unit 4. First, you will be understanding, you will be in a position to explain what is the water cement ratio and its effect on strength of concrete. And you will also be in a position to explain the gel space ratio and its effect on the strength of the concrete, and to find the strength of the concrete based on gel space ratio. This is what you will be learning by end of this module. And in addition, you'll also be in a position to explain what is the nature of strength of concrete, in the sense that how concrete gains strength with time. So all these three aspects you'll be able to explain after going through this module. So let me go to the other things, other module, other aspects of this presentation. So let's move on, guys. Go to on the hardened concrete. Right? Hardened concrete, in the sense we're talking about concrete after getting after preparing the concrete, you go for curing, right? So that is the stage we're talking about. So actually, concrete, we basically use the concrete for resisting the compressive stresses. And when you resist the compressive stresses, then it is also used as a qualitative measure for other properties of the haunted concrete. In the sense, when you know the compressive stress, compressive strength of the concrete, that can, based on the compressive strength, you will be able to say some other properties of the concrete as well. For the given cement, okay, if you take for the given cement and acceptable aggregate, the moment I say acceptable aggregates, I'm talking about the aggregates which are in good shape, good condition, and they don't cause alkyl aggregate reaction. So which probably you studied before. So we don't want those aggregates, but if you have probably acceptable aggregates and for the given cement, so these are the factors that influence the strength of the concrete. So one is ratio of cement to mixing water. So how much of the proportion? So basically we talk about water cement ratio. How much ratio you are putting, that decides the strength of the concrete. And the ratio of cement to aggregate, the proportion between cement to aggregate. So that is one thing. Then when you talk about exclusively properties of the aggregates only, that means grading of the aggregate, that means what kind of grading we are using. Are we using well graded or it's poorly graded? So what kind of grading of the aggregate you are using, that influences the strength of the concrete. Then surface structure, probably as we have already studied, whether what we have is a very smooth texture or we have a rough or glassy structure texture. So these are the factors that influence the strength of the concrete. Then we have shape of the aggregate as well. When you talk about the shape, so it could be cubical shape of the aggregate, or flaky structure, or flaky shape, or it's very rounded aggregate. So this kind of the shape, that's one more factor that influences the strength of the concrete. Then strength of the aggregate itself. That means what is the strength of the aggregate? That means strength of the parent rock from which we obtain the aggregate. And also depends on the stiffness of the aggregate particles altogether. That means modulus of elasticity of the aggregate. That also influences the strength of the concrete. Then one more thing is maximum size of aggregate. So we usually use about 20 mm is the normally used maximum size of the aggregate, but sometimes we can also go up to 40 mm based on the nature of the work. So that maximum size of the aggregate also plays a major role in deciding the strength of the concrete. To move on to next one. Okay, now excuse me. So now let's see how water cement ratio affects the strength of the concrete. So water cement ratio, as I said, basically the ratio between water to cement. How much water, how many liters of water you're adding, or how many kg of water you're adding, versus how many kgs of cement you're adding. That ratio is called water cement ratio. So example, you're adding say 200 liters of water, which is 200 kg, to say 100 kgs of cement you're adding. So basically talk about 2:1. That's what is the water cement ratio. Okay, but that's how the ratio we call it. Usually the water cement ratio we use is about 0.4 to 0.35 to 0.45. Rarely we go up 0.5. That's what the water cement ratio we usually use. Now here, let's see guys. So strength is primarily depends upon the strength of the strength of the concrete primarily depends upon the strength of the cement paste. That means when you add water to the cement, what is the comparative strength of the cement that influences the strength of the concrete. In turn, the strength of the cement depends upon dilution. Cement of the depends upon the dilution of the paste. Other words, the strength of the paste increases with the cement content. The more cement you add, you get more strength. So that's how it is. The more add water you add, that we get basically less strength. That's what we say. The second statement says the strength increases with increasing the cement content, but decreases with the increasing of cement or water content. But then it's all very arbitrary, right? The moment I say when you add water to cement, more water, less strength. So more cement, more strength. So it doesn't make much sense, right? In arbitrary terms. So that's why researchers across the world have done a lot of research, and they proposed an equation to find out the strength of concrete based on water cement ratio. Out of that, Abrams was a researcher who proposed an equation. So Abram's law says that assuming full compaction, in the sense, okay, you're not talking about partial compaction, when you do the full compaction of the concrete, and at a given age, because again, guys, concrete strength increases with age. That means you're casting a concrete today, preparing a concrete, and the strength what you check after 7 days will be different from the strength what you get after 28 days. So that means for a particular compaction and for a particular given age and the normal temperature, the temperature also plays a role. For temperature, the strength of the concrete can be taken as it's inversely proportional to the water cement ratio. That means if you take here the slide, S as the strength of the concrete, and if you take X as the water cement ratio, and you take A and B are constants, the strength is inversely proportional to the X value, basically B power X value. So that means when S is inversely proportional to 1 by B power X, so I'll take A as one more constant. So S is equal to A by B power X. That means A and B are both the constants. And for 28 days of strength of concrete, usually A and B values are taken as 96 and 7 Newton per mm square respectively. So we take it. Again, X is a factor which is nothing but water cement ratio. So you can find out the strength of the concrete based on your water cement ratio. Okay. Excuse me, guys. Now here is a graphical representation. If you look at the graphs, we have two. So first one is talks about cement water ratio. You look at the x-axis. Here also in the other graph, the next one, we have water cement ratio. So usually, normally we talk about water cement ratio. So this is rarely we use cement water ratio. So let's focus on the second diagram, where it says water cement ratio. If you look at the diagram for fully compacted concrete, this what is a fully compacted concrete. As Abram's law said that the compressive strength is inversely proportional to water cement ratio, right? Then look at the graph here. This is a fully compacted concrete. If you look at the more water and cement ratio, there will be the less strength. Example, say here. So here we have less water cement ratio, that we have more strength. The moment I increase more water cement ratio, I end up getting less compressive strength. This what is the relation between water cement ratio and the compressive strength. Okay, the solid line here, right? It says about fully compacted concrete. Otherwise, say, excuse me, say our concrete is not well compacted. For example, say you're using hand compaction and it is poorly compacted. That means it's not well compacted. If that is the case, then initially with increase in the water cement ratio, you get to see increase in the compressive strength to some extent. Thereafter, there will be decrease in the compressive strength with increase in water cement ratio. Okay. Similarly, if you are using machine compaction, the vibrators, you're using vibrators for compacting the concrete. If you are not doing very well compacted concrete, initially with increase in water cement ratio, you will see little bit of increase in the compressive strength. But then again, with increase in the water cement ratio, the compressive strength goes down. So it is. Okay. Okay. Now, guys. Typically, water cement ratio, what we use about 0.35 to 0.45 water cement ratio. If you look at the first graph, it talks about inverse proportion. It talks about cement to water ratio. It is directly proportional to compressive strength. That's why the relationship shows a linear relationship between compressive strength and cement water ratio. This is what the relation is. Okay. Let's move on to other question, other topic, guys. Hope you understood this. If you have any questions, guys, please make a note of it and post me. Probably not sure if we get a time to discuss it online. If we get, probably we'll discuss it. Other than make a note of it, we'll discuss it. Okay. Okay. Let me go back to spot. Okay. Now, second part of our discussion today is gel space ratio. Gel in the sense you are very aware that when cement, right, when you prepare a cement and add water to the cement, the hydration takes place. In the hydration process, what happens, the primary material, primary product that is generated is the gel. We call this CSH gel. That's what is the name we're talking about, gel here. And space ratio in the sense, see, when water is added to the cement, right, the hydration takes place and we'll get that water, pores are filled with water. Now, as the hydration takes place and as the curing takes place, the water gets evaporated and you get the pores developing there. In the sense, finally, what you get is a gel and the space in the concrete. So we're talking about the ratio between the gel and space here. How that ratio between gel and space affects the strength of the concrete. This is what we're going to discuss now. Now, as you know that concrete is a brittle material. So the moment I say brittle material, that means when you apply the tension force, okay, you don't see that necking taking place. Unlike you see in the steel, which is a highly ductile material. So when you apply a tensile test on steel, okay, you see that cup cone formation happening, then you see that failure happening, then the specimen fails gradually. But in case of concrete, when you apply a tension test or maybe compression, you don't see any indications. So it continue to take the load, it will fail suddenly. That's what is called brittle material. So concrete is one of the brittle materials. So its porosity primarily governs its strength basically. Just a minute, guys. Okay. So it's basically its porosity. Porosity in the sense, what are the pores? The pores are generated because hydration of the water within the cement paste or concrete that takes place. So water gets evaporated over the time, then pores are generated there. So its porosity governs the strength basically. So compressive strength is found to be severely decreasing with increase in porosity. That means if you have more pores in the concrete, then you'll find out you'll end up getting less compressive strength. So that's the purpose why we do for well compaction, and we try to minimize the pores in the concrete so that you'll get concrete with good compressive strength. On the other hand, if you have more of the pores in the concrete, then compressive strength will be decreasing. So this is what second point is said. Porosity of the concrete, which governs the strength of the concrete, is affected by gel space ratio. That means because there is a direct relation between your porosity and gel space. Okay. So the moment you get more of porosity, then concrete strength will be going down. So there is a relation between the gel space and porosity as well. So gel space ratio is how we define it is this is a ratio between the solid products of hydration. When I say solid products of hydration, basically I'm talking about CSS gel, and calcium hydroxide is also generated but basically we're talking about a gel which has cementitious properties, basically CSH gel, to the space available for these hydration products. So initially or how much space is available for these hydrated products to occupy once the complete hydration takes place. So that ratio is called gel space ratio. Okay. Again, you look at the term, guys. Gel is basically the solid portion. CHS gel, the cementitious product. What's a space? Space is basically a kind of a pores. Imagine it's a kind of porosity, kind of a pores available. That means you have more of a gel and less of a space. Then gel space ratio goes up. That means your compressive strength is high. You'll have good compressive strength. On the other hand, example, say your gel is less and means your space is more. That means overall the gel space ratio is less. Then again, you'll end up getting less compressive strength. That's how the relation is. That's what I'm saying here. The higher the gel, the moment higher the gel space ratio, the moment I say higher gel space ratio, I'm talking about higher gel, less space. That means higher CHS products and less of pores in the concrete. Then the moment I have less in the pores, that's why the porosity goes down. Therefore, the strength of the concrete improves. Okay, here is the other graphical representation between the gel space ratio of concrete to the strength of 50 cube. That means you're taking 50 cube and to get test for the different mixes. They talk about it, different mixes in the sense water cement ratio changes, cement to aggregate ratio changes, all these changes here. For different values, how this is changing. Okay. Now, here if you see gel space ratio, as the gel space ratio increases, okay, there is increase in the strength of the concrete as well, irrespective of type of mix. The rounds we are using is for mix A. Marks, this is for mix B, this is for mix C. If you look at the relation here, irrespective of type of mix, the moment you get increase in the space ratio, increase in the gel space ratio, there is increase in the strength of the concrete. When we talk about strength, we're talking about compressive strength of concrete. So the just here is a sentence, the gel space ratio, which governs the porosity of the concrete, it's affecting the strength as well, is also affected by water cement ratio. So the way, the moment, I mean, whatever we discussed in the previous topic, right? The water cement ratio has direct influence on the strength of the concrete. I said that the moment you have more of water cement ratio, the strength is reducing drastically. Okay. Again, what we are saying here is there is a relation between the gel space ratio and water cement ratio as well, because both are connected to the strength of the concrete. Okay. Let us see how it is. So, example, say you have more of water cement ratio. That means I have more of water, less of cement. Okay. The moment I have more of water, so that creates more of voids, more of pores in the concrete. That means the moment I have more of water, then I have more of space created. That's the relation. I have more of water, the more of pores are created. That means my gel space ratio goes down. In the sense, when I have more of water cement ratio, I'll have less gel space ratio. The moment I have less gel space ratio, then I'll end up getting less compressive strength. That's what the relation between water cement ratio, gel space ratio, and how they're connecting this strength of the concrete. Okay. Let me see, someone has put some chart here. I'm able to do this chart. Okay. So can't hear your voice, sir. Okay. Is it audible, guys? Is it audible now?
Yes.
Yes. Okay. 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 Let me mute all. Okay. Okay. So this is how the relation it is, guys. So again, I'm explaining one more time about the last statement. The moment you have more water cement ratio, the compressive strength is reduced because you have more of water. The moment you have more of water, there are more of voids available. So we're creating more of voids by adding more of water. The moment you have more voids, then your space available will also be more. The moment you have more space, then your gel space ratio goes down. The moment you have less gel space ratio, then your compressive strength is reduced. It's about gel space ratio. Okay. Now, let's see, guys. Okay, now what we talked about is everything in terms of very general terms. Something is increasing, something is decreasing. But let us see how we can represent them graphically. The way we have done it for water cement ratio, the relation we have established between water cement ratio and strength of the concrete. In the similar lines, let us see how we can establish the relation between the strength of the concrete and gel space ratio. Okay. So here is the equation that is proposed by a Power. So Power is a scientist. We call this a Power's equation. So he proposed an equation to determine the strength of the concrete. So based on gel space ratio. Here, this was the strength of the concrete is equal to 240 times x cubed. This was the relation proposed by him. So where x is the gel space ratio, and this 240 represents the intrinsic strength of the gel in MPa. So that's why 240 times x times cube. Okay. Okay. Some message. Okay. Now, calculation of gel space ratio. How do you find the gel space ratio? It is given by, there are two things. Whether we have a, when cement paste is completely hydrated or it's partially hydrated. There are two things. So if it is completely hydrated, in the sense that your cement is completely reacted with water, it's completely formed CSS gel and calcium hydroxide. So there is no scope for further hydration to take place. If that is the case, then gel space ratio is given by, that means the x parameter, whatever the x we have, that is calculated using this equation, 0.657 CW by so and so plus W naught. Okay, let's see what is what. Then similarly, calculation of gel space ratio if it is partially hydrated. Example, say cement is hydrated only about 60% or 70%. If that is the case, then gel space ratio is calculated using this equation. Okay, let's see what is what. What is C, what is W naught and alpha. So C is nothing but the kind of cement you have taken here, weight of the cement in grams. W naught is volume of mixing water, again in the grams, how much of water we're adding. Then C alpha is the weight of the cement that is hydrated. Example, 60%, say I have 100 grams, out of that only 20% is hydrated, then I'll take, excuse me, then I'll take 100 into 20%. That's what is my hydrated cement, weight of the cement in hasn't hydrated. So alpha basically is a percentage of hydration that has taken place. So by using these, now we know what is C, what is W naught and C alpha. So we can put those parameters here and you can find out what is the gel space ratio, whether it's a fully hydrated case or partial hydrated case. You can find out the x value. Then you substitute x value in this equation. So you'll be able to compute the compressive strength of concrete. Okay. So quickly, let us go through a numerical problem. So I had taken from the textbook directly. So it says that calculate the gel space ratio and the theoretical strength of a sample of concrete made with 500 grams of cement with 0.5 water cement ratio. And fully hydration is one case and 60% hydration is other case. So what he's saying is we have 50 grams of cement and water cement ratio what we are using is 0.5, and say it is fully hydrated. If this is the case, then tell me what is the strength of the concrete, strength of this concrete you are expecting it to be. Okay, then otherwise if it is hydration is taking place only 60%, then what is the expected strength of the concrete? This was the question. Okay, now let me take the first part and assume that it's fully hydration case. So equation is this for the proposed equation. When you substitute C is equal to 500 grams, like the way you substitute 500 plus W naught is only weight of the water you find out from this. Okay, 0.5 times of this, we know water cement ratio. So water divided by cement is 500 is equal to this 0.5 into 500 will give you W naught value. Okay, so substitute here, that means you get 250 ml, right? 250 grams. When you substitute 0.5 into 500, 250, substitute 250. The 500 plus is 0.319 into 500 plus 250. We get about 0.8. This is how we end up getting it. Again, but strength is given by 240 times x cubed. So x is this, what is our x value? Substitute x cubed, we get 123. That means for 500 grams of cement, if you're using water cement ratio of 0.5, the expected strength of concrete is 123 MPa on complete hydration. Okay. Otherwise, for the second part, it says, excuse me, hydration is 60%. If it is 60%, then I'll use this equation for finding out the gel space ratio. Substitute 500 into 60% because 0.6 I'm multiplying, only 60% is hydrated. So 60% is nothing but 0.6. Here also same thing, multiplying with 0.6. This is one parameter. This is not 0.319 into C alpha. 0.319, C is 500 grams, alpha is 60% hydration, plus W is 250. 250, how I got is, this water cement ratio is equal to 0.5. Water is equal to 0.5 into cement. Cement is 500. So I get 0.5 into 500, you get 250. That's what is this 250. So this way I get gel space ratio as 0.57 for 60% of hydration. That though, therefore, I get a theoretical strength is nothing but 240 times x cube. Substitute x is equal to 0.57 times cube. So I get the strength of the concrete. So this what is the expected strength of the concrete when you have excuse me 60% of hydration for water cement ratio of 0.5 and 500 grams of cement. This is how it is. Okay. Okay. Now let's move on to the next topic, guys. We're done with the. Okay. Someone has a question. Let me see how to. Oh, just a moment. Someone raised hand. Wanted to see. Okay. Just waiting. Someone is waiting. Just a minute, guys. Admit. Okay. Just a minute. Yeah, someone is asking question here. Samyukta. Samyukta, can you hear me? Samyukta, you have a question? Samyukta?
Sir.
Yeah, you have a question?
No, sir.
I think you raised your hand. All of you, just a moment. Okay. Okay, guys. So let's continue our discussion. So talking about gel space ratio. So basically, there's a lot of difference between, but practically the equation will give you the strength of the concrete. But then there is a lot of difference between the theoretical and actual strength of the concrete. In the sense that by using the equation, if you find the strength, using the 250 times x cube, you get some strength. But if I test the concrete specimen for the same water cement ratio and similar weight of concrete, the strength will be different. So because we don't get actual strength as we got in a computed theoretical equation, the reason being that there will be a lot of discontinuous such as voids in the concrete that you have prepared, or there could be fissures in the sense like some cracks, then could be bleeding could have happened, or there could be rupture of the bond or drying shrinkage or anything, temperature changes, lot of things. That's why whatever theoretical value we get through the equation 250 times x cube may not be exactly the same as we get practically, in the sense when you do the testing of a concrete, the values may not match because of all these reasons. Okay. But usually what is found was actual strength of the concrete is found to be less than theoretical value. In the theoretical value, we'll assume that 100% compaction, no shrinkage, temperature stresses we don't consider bleeding and all. So that's why we, actually our theoretical value is found to be a little higher than the actual strength. Other way around, actual strength is found to be usually less than the computed theoretical values. Okay, now let's move to the third part of our discussion, guys. We talk about nature of strength of concrete. Okay, so nature of strength of concrete is, we know, right, the moment you add water to the concrete, a hydration takes place. Then hydration continues. Then we do the, we'll talk about it, the curing part later. So basically, excuse me, concrete gains strength with the time. Basically, the more time you allow for the hydration to take place, the concrete continues to gain strength. That's what we're talking about, nature of strength of concrete. It develops the strength with continuous hydration. But the rate of hydration is very high initially. That's why rate of gain of strength is faster initially and it's get reduced with age. The moment, that means if you prepare a concrete today, by heat of hydration is very high initially. Thereby rate of gain of strength is very high initially. Then you test, say after 10 days, the difference between 10th day and 11th day, the rate of gain will be less as compared to the rate of gain we have seen for first day and second day. And that's what the second statement says. The rate of gain of strength is reduced with the process of time, with the age. But usually, right, what we assume is, usually we take it for granted that concrete assumes to attain 28 days strength. That means we assume that concrete gains its complete strength in 28 days, full strength in 28 days. 28 days. See, guys, let me give you a small explanation here. See, even in your design of reinforced concrete structures, you take FCK value, right? FCK is example, say, talking about M20 grade concrete. We take FCK as 20 Newton per mm square. So we'll assume that the 20 MPa, we gain the 20 MPa within 28 days. That's it. Exactly 28 days of age of concrete. We'll assume that, excuse me, we gain the 20 MPa. But in practice, but in reality, what happens is the concrete continues to gain strength even after 28 days of its age. But its value is not phenomenal if we talk about regular mixtures, regular ingredients, like normally if you're using only cement, fine aggregate, coarse aggregate, and water, to some extent some admixtures. Then after 28 days, we don't see the substantial increase in the strength. However, there will be increase in the strength if you use normal ingredients. But however, we'll assume that concrete gains complete strength in 28 days itself. Okay. So here some codes, what we follow is Indian standard code. But if we talk about other codes, I'll come back to Indian standard code, what it says. Before that, so there are some other codes in the world who that permit the age of the concrete. The taking the increase in the strength with age of the concrete. That means if you are allowing the concrete to cure for about say 56 days or 90 days, you can take more strength in the design. In FCK, say for suppose you're using M20 grade concrete, in the design we take FCK as 20. Okay? Assuming that in 28 days it's gaining complete strength. But there are some cores that allow, okay, because you're not taking 28 strength, you take more strength, more days. That's why instead of taking 20, you take 22, you take 25. Like that, there are some codes that are allowing. For example, I'm putting one such code here. It's a British code. So British code, if you look at here, so minimum age of member when full design load is applied in months. Example, say 1 month. That means immediately after 1 month of casting the element, in the sense a beam or concrete, we'll assume that it's a one factor. That means one in the sense completely attained. Example M20 is attained 20 MPa. That's it. Additional strength is nothing. Example, say 2 months. 2 months in the sense 60 days after casting it. So usually it's supposed to be one only, but he is taking 10% extra. 10% extra. That means if it is 20 MPa, multiply 20 with 1.1. So get maybe 22 MPa. Will allow to take. That means designer is also is allowed to take 22 MPa instead of 20 MPa after 2 months. If he's putting the load on the structure after 2 months, the designer is allowed to take 22 MPa instead of 20 MPa, which is gained in after 1 month. So likewise, based on the age, based on the months after its casting, so we can use the different factors, age factors, for low strength concrete and high strength concrete. We can use the factors and take the increase in the strength in the design. One such is British code that allows it. But when it comes to Indian standard code, so what code says is, so previously, see, we use IS 456-2000, right, for our design of reinforced concrete structures. But there was a code, same code before its revision. It said that it considered the age factor. That means, okay, with increase in the age, because concrete is gaining the strength, we use the increased strength in the design. It allowed it, but then it increased strength only allowed in the lower columns of the multi-story buildings. It was the case. But now the revised version, the IS 456-2000, what it says is, let me read it out for you, then I'll explain this. There is normally a gain of strength beyond 28 days. So it's accepting that, yes, there is a gain of strength even after 28 days of casting the concrete. However, the quantum of increase depends upon grades. That means grade of the concrete you're using, that means grade of the cement you're using, and type of cement. So whether what kind of cement is it? Different types of cement. So there are 20 types of cement is there. whether it's a OPC type or PPC type, or we're using early strength concrete, early set cement, ready set cement, whatever the kind of cement you're using. Then curing depends on what kind of curing you're doing. So we'll be discussing in detail about the curing methods, but then whether curing is water curing or using pressure or using membrane or curing type. Then environmental conditions. So what kind of environment? We have mild environment, marine environment, all those environment. So what he's saying is concrete gains strength after 28 days. There's no doubt about it. But then how much it gains, the amount it gains, the gain depends upon all these factors. The design should be based on 28 days characteristic strength. That's what I'd say. That's the reason why in your DDRC, design of reinforced concrete structures, you take FCK as, example, say using M20 grade concrete, you take it as FCK is 20 MPa only, because that's what code says. So it says that you take only 28 days strength in your design, unless there is evidence to justify a higher strength for a particular structure due to age. That means if you are using different materials, as a concrete specialist, if you know that, okay, concrete is going to gain strength substantially even after 28 days, then you take that strength. That is, even if you are able to justify. So we'll be able to justify provided if you use different materials. So probably, I think you studied, right? Probably if you use silica fume, or especially if you use fly ash, those materials along with the cement, the fly ash has a property to gain strength in long term. Maybe after 60 days, after 90 days, you see that more strength if you use a fly ash. So likewise, if you're using any extra materials, okay, which can add more strength in long term, then you can use those cases. In those cases, you can use the later strength, maybe 60 days strength in the design or 40 days strength in the design instead of 28 days strength. That's what court says. Court says that unless there is a justification or evidence to justify, then only use that increased strength. Otherwise, you restrict your strength of the concrete to 28 days strength. Okay, it's about nature of the strength of the concrete. Okay, now what we talked about is again general terms. Okay, as an engineer, we'd like to see some equations. We'd like to see some mathematical equations to predict the strength. Okay, so that's what is the next step. Here, if you look at this, nature of strength of concrete. Again, see, it's necessary. Sometimes it may be necessary to estimate your 1 day, 3 days, 7 days strength. Early, you would like to estimate the strength. Okay, so the relation between strength of the concrete at lower age, when I say lower age, 1 day of age, that means after casting the concrete, immediately after 1 day, how much strength it is getting, it is gaining, or maybe after 3 days, how much strength it is gaining, or maybe after 7 days of its casting, what is the strength of the concrete? We'd like to find out, okay? At lower age and 28 days, either it's the early stage, whether you want to find out the strength at these days, or maybe 28 days, basically depends upon these three factors. One is compound composition of cement. The moment I say compound composition, I'm talking about oxide compounds. We talk about a lot of oxides, right? In the cement, talk about we have silica, we have iron oxide, alumina. So what is the oxide compounds of the composition of the cement? Then fineness of grinding. What is the particle size of the cement? And then temperature of the curing. At what temperature you're doing the curing. So these are the main factors that influence the strength of concrete at 28 days or maybe in the early age, first to 7 days strength. So these are the factors that influence. And there is a established relation between the 7 days and 28 days of concrete. Example, say I cast a concrete specimen today. I took a specimen. I found the strength of concrete after 7 days. I would like to find out what is the likely strength of concrete after 28 days. So we can use these equations. The equation says is if 28 days strength of concrete is equal to 1.4 times of strength of concrete in 7 days plus 150 and 1.4 times F7 into 850. I mean, it varies between these two values. It anywhere between this value to this value, that would be the likely strength of concrete. The units, be careful, guys. You're talking about pounds per square inch. This is what we get strength of the concrete. It's not in MPa. It's not in Newton per mm square. Okay. That means if you know strength of concrete for 7 days, you can compute it for 28 days using these equations. The value lies between this value and this value. That's where it lies. Okay. Okay. Oh, one more thing. Sorry. So on one other relation between you have 7 days strength and 28 days strength is one more equation. Again, K1, K2 are the constant, they're the coefficients. The value usually ranges again between K1 value 0.3 to 0.8 and K2 value ranges from 3 to 8, 3 to 6. So these are ranges. So if you know F7 value, compressive strength of concrete after 7 days, you can compute compressive strength of concrete after 28 days. That's what we can do. Okay. So thank you guys. This what is the lecture I have for today. So if you have any questions, I think I'm just unmuting all of you. So if you have any questions, feel free to ask. Or else maybe not be now. If you have, after going through this video, after going through the PPT, if you have any other question, text me, put me on WhatsApp. You can even send me to my email. Okay, I'll stop for now. So any of you have any questions? Please ask the questions, guys. Any questions so far? No questions, guys? No questions? Okay, guys, if you don't have any questions, I'll turn off. Okay, I'll stop the video. Then all of you go through the lectures, go through the textbook. Anytime if you have any question, text me on WhatsApp or you can send out me an email. Okay. So for further lectures, I'll
Okay.
be posting you the dates on the WhatsApp. Keep checking your WhatsApp. Maybe tomorrow I'll take class again. I'll send you the time. Okay. I'll try to finish up the fourth unit. Okay. So any other thing you would like to share, guys? Anyone would like to share anything? No?
No.
Okay. Okay. Thank you, guys. Thank you for joining this lecture, and see you tomorrow again. Okay. Thank you, guys.
Thank you, sir.
Thank you.